Hello friends, this is my second lecture on random variables. In the last lecture we have discussed what is meaning of random variable and we have discussed the formal definition of random variable also. Also we discussed that there are two types of random variables, discrete random variables and continuous random variables. So first we will focus on discrete random variables and then we will discuss continuous random variables. So in today's session we are going to discuss probability mass function of a discrete random variable. As we discussed in the last lecture, a discrete random variable is a variable whose range is finite or countably infinite. So the range of discrete random variable is at most countable. Before discussing probability mass function, we require some standard notations. So first we understand some notations which are required for further discussion. So suppose X is a random variable where this capital S is a sample space. Then this set of all outcomes in the sample space such that value of random variable is small x at those outcomes. So this set is a subset of the sample space. We are collecting those outcomes in the sample space whose image is small x. So this set is a subset of the sample space capital S. And we know that any subset of sample space is known as event. So this set is an event in S. So every time we will not write this whole set. For briefly, we will denote this event by this notation. Capital X equal to small x. So capital X equal to small x is not an equation, it is the simple notation for this event. Capital X equal to small x represents the event. Which event? So the event is the set of all outcomes in this sample space whose images are small x. For example, suppose we have this is sample space S and suppose X is somewhere here, and suppose there are 3 or 4 outcomes in the sample space. Suppose this outcome is omega 1, this is omega 2. So if image is of omega 1 and omega 2, if image of omega 1 and omega 2 under random variable x are small x, then this event capital X equal to x will contain 2 outcomes. So omega 1 comma omega 2. So this is nothing but this event capital X equal to x. We have 4 outcomes in the sample space, but we are collecting those outcomes whose image is x. So there are 2 outcomes, omega 1 and omega 2, whose image is under random variable x is small x. So this omega 1 comma omega 2 is nothing but this event capital X equal to small x. So instead of writing this big set every time, it will be denoted by this notation capital X equal to small x. So please keep in mind, capital X equal to small x is an event in the sample space S. It is not an equation. Which event? So it is that event which contains those outcomes in the sample space whose image is real number x. Similarly, this event, the set of outcomes in the sample space whose image is less than or equal to x is denoted by this notation. Capital X is less than or equal to x. So capital X less than or equal to x represents the event omega belongs to S such that x of omega, that is image of omega, is less than or equal to small x. And this is also similar to these two. The event omega belongs to capital S such that x of omega is in this interval, open close interval AB, is denoted by a less than capital X less than or equal to b. Okay. Instead of writing in this way, we can write in this way also. X of omega image lies in the interval open close interval a to b. Okay, so both are similar. So keep in mind these notations. Every time we will not write down these big sets, we will just write down this type of notations. So capital X equal to x represents this event, capital X less than or equal to x represents this event. Similarly, a less than x less than or equal to b is the set of those outcomes in sample space whose image is in open close interval a to b. Let us try to understand what is meaning of probability mass function. So probability mass function is defined for discrete random variable. So we start by taking any discrete random variable. Suppose x is a discrete random variable defined on the sample space capital S. Then the probability mass function of x is denoted by small p of x. Some authors are denoting this PMF by this notation also, p of x suffix x, to indicate that it is the PMF of random variable x. Okay. Or we can simply write p of x also. But if there are more than two random variables, then it is denoted by this notation to show that it is PMF of particular random variable. So PMF is denoted by p of x, and it is a function such that these three properties are satisfied. So what is p of x? How it is defined? So p of x is nothing but probability of this event x equal to x. So x equal to x means the set of those outcomes in sample space whose images are small x. So for each x, which is the value of random variable, we can find out probability of this event. Corresponding to each value of small x, we can define this event, and probability of that event is the value of probability mass function at point x. So probability mass function at point x is given by probability of this event, and it is defined for every x. Second property is p of x is always non-negative for every x. We know that probabilities are always non-negative. And third property is for each x, if you count probability mass function for each x, then sum of all the values of PMF is always 1. So the function which satisfies these three properties is known as probability mass function of a discrete random variable. Another name for probability mass function is discrete density function. Some authors are using this another name also. Instead of probability mass function, we can say that it is discrete density function. Now once you define probability mass function, you can write down probability distribution also. So probability distribution means for each value of random variable we can assign probabilities. So that distribution, random variable, each value of random variable has probability. So if we are writing the table values, in one row we are writing values of x, and corresponding values of probabilities are written below that row. So that type of distribution is called probability distribution. So a probability distribution for a discrete random variable is a mutually exclusive listing of all possible outcomes for that random variable such that a particular probability of occurrence is associated with each outcome. So instead of going for this formal definition, we can just understand that probability distribution is the distribution of probabilities for each value of random variable. Some authors are considering this probability mass function. The definition of probability mass function is considered as probability distribution also by some authors. So that is also fine. We can consider this as a definition of probability distribution also if required, because what we are doing, we are just assigning probabilities to each value of random variable x. So this p of x is the probability mass function, and if we are writing in this way, here values of random variable and in another column values of probabilities. So this type of distribution is called probability distribution. Here we can write values of random variable. For x1, suppose value of probability mass function is p of x1. For x2, probability mass function has value p of x2, and so on. So if we write down for each value of random variable, if probabilities are assigned, these probabilities will be assigned by using probability mass function. So this type of distribution is known as probability distribution. So we consider one example how to write down probability distribution or how to find out the probability mass function. Find the probability mass function of the number of heads in tossing a fair coin 3 times. So in this example, the random experiment is tossing of a coin 3 times, and the random variable is number of heads. So how we can consider random variable in this example? It is defined as image of any outcome omega is nothing but the number of heads appearing in that outcome. So for each outcome in the sample space, we can count the number of heads in that particular outcome. Before that, we must know what is the sample space. So the random experiment is tossing a coin 3 times. So we know how to find out sample space of this experiment. For each toss, there are only 2 possibilities, either head and tail, and we are tossing a coin 3 times. So sample space is nothing but Cartesian product of these 3 sets. So it is clear to all of you that how we are writing this sample space. First we are taking Cartesian product of these 2 sets and then Cartesian product of these 2 sets. So there are total 8 outcomes in the sample space. Now for each outcome we can find out value of random variable. For example, if I want to find out value of random variable for this outcome, or if I want to find out image of this outcome under random variable capital X, then random variable is number of heads in the outcome. Here outcome is HHH, so value of random variable at this outcome is 3, or image of this outcome under random variable X is 3. Similarly, we can define for each outcome the value of random variable we can define. For example, image of this outcome is 2 because there are 2 heads here. Image of this outcome under random variable x is 0 because there is no head in this outcome. So the maximum possible value of random variable is 3. Okay, there are 3 heads possible. Maximum heads possible are 3 because we are tossing a coin 3 times. And minimum value is 0. If there is no head in any of these tosses, then we can say that value of random variable is 0. So the possible values of random variable are 0, 1, 2 and 3. So we have to find out probability mass function for each value of this random variable. So by the definition, probability mass function is defined as P of x equal to probability of this event, capital X equal to small x, and here x runs from 0, 1 to 3. So first we take x equal to 0. Now capital X equal to 0 is the event. Which event? So we have to find out those outcomes in the sample space whose image is 0. Now x of omega means number of heads. So what does this mean? This means that number of heads are 0. That means there is no head in the outcome. So we have to find out that outcome in the sample space in which there is no head. So this is the only outcome in which there is no head. All are tails. So probability of this event TTT, that means head occurs in all the 3 tosses, is 1 by 8 because outcomes in favor of this event is 1 and total number of outcomes are 8. Now suppose I want to find out value of PMF at x equal to 1. So P of 1 equal to, by this definition, here I put x equal to 1. P of 1 equal to probability of this event x equal to 1. So I have to find out those outcomes in the sample space whose image is 1. So x of omega equal to 1 means there is only one head. So I will search those outcomes in the sample space in which there is only one head. So here there are 3 heads, here 2 heads, here also there are 2 heads. In this outcome we have only one head. There are 2 heads here. In this outcome there is only one head, and this is also the outcome in which there is only one head. So outcomes in which there is only one head are indicated by this arrow. So those we have written here. So there are 3 outcomes in favor of this event. So probability of this event is 3 by 8. Similarly, you have to find out P of 2. So P of 2 means probability of that event such that number of heads are 2. So I have to find out those outcomes in which there are 2 heads. So that we can find out, again we have to search for 2 heads. So this is containing 2 heads, this is also containing 2 heads, and this is also containing 2 heads, and there is no other outcome which contains 2 heads. So again there are 3 outcomes in favor of this event. So probability is 3 by 8. Last one is probability that capital X equal to 3 means there are 3 heads. So outcomes in favor of 3 heads is only one outcome. So probability is 1 by 8. So in this way we can easily assign probabilities to each value of random variable, and that will decide our probability mass function. So in this case the PMF of x is P of 0 is 1 by 8, P of 1 is 3 by 8, P of 2 is 3 by 8, and P of 3 is 1 by 8. So here this is our probability mass function. It is not necessary that PMF will always be in this form. Sometimes we can have the formula for probability mass function of random variable also, that we will see in the upcoming lectures. Now if I want to write down probability distribution for this random variable, then I will write down these values in table form. So values of x are 0, 1, 2 and 3, and here I have written corresponding probabilities. So for 0 probability is 1 by 8, for 1 it is 3 by 8, for 2 3 by 8, and for 3 it is 1 by 8. So this is our probability distribution. Let us take another example to find out probability mass function of a discrete random variable. So in example 2, what is given? 6 boxes of components are ready to be shipped by a certain supplier. There are 6 boxes of components. The number of defective components in each box is given in this table. So in box 1 there are 0 defective components. In box 2 there are 2 defective components, and similarly for others defective components are given. Now what is experiment? Experiment is one of these boxes is to be randomly selected for shipment to a particular customer. So random variable is to select one box out of these 6 boxes. So that we can do in 6 ways. If I want to select a box out of these 6 boxes, then there are chances that we can have box 1 selected, 2 selected, 3, 4, 5 or 6. So there are 6 possibilities. So the total number of outcomes in favor of selecting a box out of these 6 boxes is 6. What is random variable? Random variable x is the number of defectives in the selected box. So you can see here the maximum number of defectives are 2 and minimum number of defectives are 0. So possible values of the random variable are 0, 1 and 2. And we have to find out probability mass function of this random variable x. So again I repeat, the random experiment is to select one box out of these 6 boxes. So total number of outcomes are 6. Random variable is number of defectives in the selected box, and it is given that maximum number of defectives are 2 in any box and minimum number of defectives are 0. So in box 1 it is given that there is no defective. In box 2 there are 2 defectives. In 3 and 6 there are 0 defectives. In 4 there is 1 defective, and there are 2 defective components in box 5. So we have to find out probabilities for values of x which are 0, 1 and 2. So here I have written, here the experiment is to select one box out of 6 given boxes, which can be done in 6C1, that is 6 ways. So the total number of outcomes are 6. The random variable x is the number of defectives in the selected box. So the possible values of capital X are 0, 1 and 2 as I discussed. Now by definition P of x equal to probability of event capital X equal to small x, and here x runs from 0, 1 and 2. So let us find out probability for each value of small x. So by definition, if you put x equal to 0 here, then the value of probability mass function at x equal to 0 equal to probability of this event x equal to 0. So capital X equal to 0 means there is no defective in the selected box. what does this represent? Capital X equal to 0 means capital X is number of defectives in the selected box. So capital X is 0, that means there is no defective component in the selected box. So we have to find out those boxes in which there is no defective component. So again from the table we can see that box 1 has 0 defective, 3 has 0 defective, and box 6 has 0 defective. So the event that there is no defective in the box is equivalent to the selection of box 1 or box 3 or box 6. If we select box 1 or box 3 or box 6, then there is no defective item. So this event, there is no defective component in the selected box, is equivalent to this event. Which event? The selected box is either box 1 or box 3 or box 6. Now there are 3 events here, either box 1 is selected or 3 is selected or 6 is selected. But we are selecting only one box at a time. So if box 1 is selected, there are no possibilities for box 3 and 6 to be selected. So in short, there are 3 events here and all the 3 events cannot happen at the same time. That means these 3 events are mutually exclusive. So probability of these 3 events equal to addition of their probabilities. So probability of box 1, 3 or 6 equal to probability of box 1 plus probability of box 3 plus probability of box 6, because these 3 are mutually exclusive events. Now probability of selecting any box is 1 by 6, because we are selecting only one box. So this is nothing but 3 by 6 and we can cancel out 3. So probability of this event capital X equal to 0 is 1 by 2, or the value of probability mass function at small x equal to 0 is 1 by 2. Similarly, we can find out P of 1. P of 1 means probability that capital X equal to 1. So what is this event? Capital X equal to 1 represents the event that there is one defective component in the selected box. So again I have to search in the table which box contains only one defective. So you can see box number 4 has only one defective. So the event that box 1 is event that there is one defective in the selected box is nothing but the event that box selected is box number 4 and its probability is 1 by 6. Similarly, P of 2 equal to probability that there are 2 defectives in the selected box. So again we have to search which 2 boxes has 2 defectives. So number 2 and 5. Box number 2 and 5 have 2 defectives. So that event is equivalent to the event that this event, 2 defectives in the selected box. This is equivalent to the event selected box is box 2 or box 5. Again these 2 are mutually exclusive events. So probability of box 2 or box 5 is nothing but probability of selecting box 2 plus probability of selecting box 5, and probability of both the events is 1 by 6, so it is 2 by 6. So in this way we can decide probability mass function of a discrete random variable. So this is about today's lecture. In the next lecture we will discuss distribution function or cumulative distribution function of a discrete random variable. I hope you like this lecture. Please subscribe my channel for more lectures of this subject, probability and statistics. Thank you very much.